Well, it's a pleasure to introduce the first spotlight session. We have a batch of 11 papers. I think, well, 11 presentations. I've seen most of the presenter. Please sit like somewhere you can access like easily the laptop. And as soon as the previous presentation is coming, then please come up. That would be like roughly 1 hour of spotlight, and then you'll be able to discuss with the presenter on the other side of the room. There is nothing on this slide, right? I can just... So the first presenter is going to be Florian Schmid, and then I'll let you roll with that.
Hi everyone, my name is Florian Schmid and I'm a PhD student at Johannes Kepler University Linz. In this short presentation I'm giving you an overview of the paper Distilling the Knowledge of Transformers and CNNs with CP Mobile. Our paper is an in-depth study of the top-ranked system that we submitted to this year's challenge Task 1. Task 1 is about acoustic scene classification. So in this task, we have to come up with a system that can classify an audio recording into 1 out of 10 different acoustic scenes. The challenge comes with 2 major difficulties. The first one are the low complexity constraints and ranking. So we have to develop models with a good performance complexity trade-off. And the second one is cross-device generalization, which means we have to develop models that can generalize to recording devices that are not included in the training set. So we tackle the first difficulty with improved teachers and a more efficient student in a knowledge distillation setup, and the second one with frequency mix style and device impulse response augmentation. Let's start by talking about this device impulse response augmentation. We artificially increase the recording device variety in the training set via convolution with an external set of impulse responses. For this, we download 66 freely available DIRs from MIC-IRP. You can see one such microphone on this slide, its impulse response and its frequency response, and we convolve the audio recordings in our training set with these impulse responses to artificially increase the recording device variety. If we talk now about the knowledge distillation setup, we improved the teacher ensemble based on 2 key insights. We ensemble models trained with varying device generalization settings, and in particular, a large performance boost comes from ensembling transformers and CNNs. In this table, you can see that we used a CNN called CP-ResNet and a transformer model called PAST. We use different configurations regarding the device generalization, frequency mix style, and DIR augmentation. And if we cleverly ensemble multiple of these configurations, we can get up to an accuracy of 68 percentage points, which is an increase by more than 5 percentage points compared to last year's top-ranked systems teacher model. The most important improvement that we introduce is a very efficient student model called CP Mobile. We start from the well-established CP-ResNet, which has performed really well in previous editions of the challenge, and it has important properties like the regularized receptive field. We aim to keep these properties, but make the architecture more lightweight. In particular, we factorize its 3x3 convolutions into inverted bottleneck blocks that consist of cheaper pointwise and depthwise convolutions. We replace the max pools in the CP-ResNet with strided convolutions, which has shown to increase the model's capacity. We further remove costly shortcut paths and split the input convolutions, mainly to save computational effort. And finally, we integrate global response normalization to enhance the feature diversity. Finally, it remains to have a brief glimpse on the results. So we can scale the CP Mobile in our setup down to 5.7K parameters, so a really tiny model. And we still beat the DCASE baseline, which is about 8 times as large by 10 percentage points in accuracy. And we can match last year's top-ranked systems accuracy with only 1/10 of its parameters. I'm very happy to discuss more results in an in-depth ablation study with you at the poster. Thank you for your attention.
I think it's not working on Keynote. Control and control. Control. Sorry. Okay. Hello, I'm Minsung Kang from Gaudio. Today I'd like to introduce our Foley sound synthesis model, Foley, which has on second place in Task 7A of DCASE 2023, along with our innovative training strategy for generative audio AI. In recent days, we can't imagine movies and games without a realistic sound. So, creating proper sound is a vital and intricate job, but it is very labor-intensive and expensive. That's where Foley steps in. Our model could effortlessly generate high-quality audio from natural text, which could transform sound production industry. Foley employs a cascade model architecture, inspired by the successful image generation models like Glide, DALL-E 2, and Imagine. We divided the MER spectrogram generation stage into two steps. Low-resolution spectrogram generator, followed by a spectrogram upsampler. And then, by using the MER inversion network, the MER spectrogram is converted into an audio signal. To control the audio quality, we add an audio quality token at the start of the prompt corresponding to dataset quality. Since a large portion of our dataset includes low-quality samples, without this prompt strategy, low-quality audio will be generated inevitably. This prompt strategy empowers our model to make high-quality audio consistently. These are samples generated by Foley. Both spectrograms stem from identical prompts, differing only in the audio quality token, clean and noisy. As you can see in the picture, the clean MER spectrogram exhibits a broader range of frequency range and effectively mitigate the noise interference, while noisy MER spectrogram intentionally produces noise. Finally, here are audio samples from Foley. Actually, I want to hear our samples, but now you can see our poster session. And in conclusion, so Foley achieves a high audio quality through its cascade model architecture and audio quality prompt strategy. For a deeper dive into the specifics, please refer to our comprehensive paper linked on the left. And to utilize our MER inversion network, you can access our pre-trained model through the link on the right. If you have any more questions, please feel free to come by my poster session. Thank you for your attention.
Hello everyone, I'm Huang, and I'm going to give a brief introduction of our work on crowdsourcing and evaluating text-based audio retrieval relevance. And in this work, we are focusing on the problem about audio text relevance in the task text-based audio retrieval. And this task is about searching for audio clips relevant to a given text query. And the relevance between audio clips and text queries is usually assumed to be binary. So an audio clip can be relevant or irrelevant to a text query. and there is no annotated non-binary relevance in the existing audio text dataset, such as relevance graded at varying scales. And in this work, we crowdsourced non-binary relevance between audio clips and text queries. So we conducted our crowdsourcing work on the Amazon Mechanical Turk platform, and the first step, we selected the audio clips and the captions for relevance assessment, and we choose audio clips and captions from the closed dataset. And then we combine 1 caption and 5 audio clips to form a single crowdsourcing task, which is named as a hit on the Amazon Mechanical Turk platform. And every hit is assigned to multiple cloud workers. And the cloud workers are asked to grade audio clips by answering the question about how much the thought content of the audio clip matches the description of a caption, the description of a caption. And all the valid answers from the cloud workers are aggregated to form the final non-binary relevance data. And the main outcome from our work, we crowdsourced non-binary relevance for audio clips and their existing captions, which are selected from the closed dataset. And we have released our crowdsourced data and the crowdsourcing task instructions on GitHub. And we also experiment with the crowdsourced non-binary relevance and also binary relevance defined by the audio caption path in our experiment. Thank you.
What is the command again? Control L? Yeah. Okay, thank you. Hi everyone. I am Ilyas Mohamed. I'm a PhD student at IMT Atlantique in France. I'll be presenting to you our work with Romain Cerisel and Nicolas Farugia, entitled Pretraining Representations for Bioacoustic Few-Shot Detection using Supervised Contrastive Learning. So this work summarizes our submission to task 5 of this year. A quick reminder of the task challenge. We have an audio recording of animal vocalization, and we are provided with 5 annotations of an event of interest, and the idea to have a few-shot system that will learn from these 5 annotations and will predict the other instances of this event of interest in the remainder of the audio recording. In order to do that, we propose our approach that consists in a first step of pre-training of a good feature extractor using the contrastive learning framework. So the idea of the contrastive learning framework is to learn an embedding space where we have pairs of similar samples that are pulled together and pairs of dissimilar samples that are pushed apart. So we can have 2 scenarios. Either we are working with unsupervised data. In this case, we will create the similar views using data augmentation and consider all the other examples in the batch as negatives. Or if we are using data labels, as in our work, we can use label information in order to select the positives and the negatives. And on top of that, in practice, we also use data augmentation that helps to converge faster and learn good invariances. So for this example right here, we have the sound of the bird that we call an anchor, and we are selecting another sound of the same class that we call positive. And then all the other examples in the batch are considered negatives. So for example, we have a batch of size 5. So what we want to do is we want to maximize this quantity over here, where we have in the numerator the similarity between the anchor and the positive, and in the denominator we have all the similarities of that anchor. So this is for just one example. And all the other examples in the batch will play the role of the anchor, and we will have to select the positives and negatives for each one of them. And we will optimize for all of this using gradient descent. Once we have trained the feature extractor, we'll move on to the validation set. And here we will consider the 5-shot scenario where we have audio recording with 5 annotations. And we want to train a binary classifier that will learn to detect presence and absence of the event of interest. We will simply slide a window after the 5th event and make predictions for the windows. And that way we will predict, infer onsets and offsets of the other instances. We make no post-processing in our method. And for the validation set, we will play around with hyperparameters and pick the best ones. And once they are fixed, we'll move on to the test set and do exactly the same as in the validation. What we can take on from our work is that data augmentation is pretty crucial for contrastive learning. And this contrastive learning framework uses pretty good feature extractor that will generalize to outside the domain of training, because here we have different species in the validation and test, different than from the ones in the training set. And a simple linear classification achieves competitive performance, and we got an F-score of 63% in the validation and 42% for the test set. And this results in a system ranking second in the challenge. I thank you for your attention, and I invite you to visit our poster 4 to learn more about our method. Thank you.
Hello, I'm Chon, the presenter of early sound synthesis based on generative reversal networks using oneself-conditioned contrastive learning. Then I'll start the presentation. In media outlets such as movies, dramas, and advertisements, there are not only character voices, but also surrounding environmental sounds such as footsteps and car horns. These surrounding environmental sounds are not suitable for using sound recorded directly in the field due to a number of other noises. Therefore, sound experts produce sound suitable for the situation in the studio, which is called Foley sound. Foley sound serves to convey the situation more vividly in various media outlets. The goal of this research is to automatically generate user-desired Foley sounds using generative model. We used Foley sound dataset provided by DCASE challenge. The dataset is a small dataset with 800 or less data per class. The scarcity of data is likely to lead to a problem with a lack of diversity in the generated data. In this work, we present a method for solving the problem encountered in generative model training using small dataset. We use GAN as generative model. The problem with GAN is instability of training. Control GAN and C-sequence GAN improve the instability of GAN training by introducing contrastive learning that minimizes the distance between data embeddings belonging to the same class and maximizes the distance between data embeddings belonging to different classes. However, when these models are trained on small data set, overfitting of discriminator occurs, which quickly breaks the balance of training between the generator and discriminator, resulting in a significant decrease in the diversity of generated data. To improve this problem, we propose oneself-conditioned contrastive learning, which maximizes distance between all data embeddings, regardless of whether the data belonging to the same class or different classes, and only minimizes distance between data embedding and one's class embedding. We conducted experiments to prove the effectiveness of oneself-conditioned contrastive learning. First, the embeddings of generated data in the latent space of discriminator were visualized. It can be seen that the distribution is more expanded on the right side than on the left side of figure 1. This means that the diversity of generated data has increased while generated data are well classified. Secondly, the results of applying oneself-conditioned contrast learning to Contra-GAN and Sisukon-GAN, respectively, were compared, and it is shown in Table 2. Models to which oneself-conditioned contrast learning was applied more than doubled the FAD value compared to models to which was not applied. Finally, we compared our model with the baseline given in the challenge. We demonstrate that our model achieves better performance than the baseline, and our model ranks second in task 7B of the DCASE challenge. Thank you.
So hello, I'm Mark Plumley from University of Surrey, and I'm here talking on behalf of Jinbo Hu and Ian Sao, who couldn't make it today. I'll be presenting on meta-celled, meta-learning for fast adaptation to new environment in sound event localization and detection. So this is related to one of the DCASE tasks on sound event localization and detection. And here, the system that we presented and applied to the DCASE 2022 challenge, we did quite well in that challenge. We got a second rank in the challenge, so we're doing something that's doing roughly right. But when we looked at in detail about the performance, we found that some of the rooms in this had poor performance. So if you look at room 2 that's highlighted here, particularly the localization error, which is in the middle, we found the localization error was very poor. So in this data set, if we think about the data and that's being collected, there's a picture of the sort of room here. What's going on? We're recording this with 32 channel microphones, motion capture system, 360-degree camera, so on. This is a very expensive thing, and it happens in lots of different rooms. So we've got a system which is working in most of the rooms that things have been recorded in. The rooms in the test set are all unseen, but 1 or 2 of those rooms, the system's not working. So if we think about what we're usually training systems to do on a task, we usually think of a task as, here's an input audio example, here's the answer. That's the task. And we have to train a system in order to solve that task. But actually, if we look at what this task is, what we're now given, for each new room, we've been given a few labeled examples in order to adapt to that room. And then we've got the rest of the unseen examples in that room. So actually, we've got a slightly different task here. The task is now, given a small number of training examples on this room, let's test it on the remaining unseen examples on that room. So that really corresponds to this task at the bottom. This is a new type of task, and that means that we need to learn a system to solve that task from lots of training examples of tasks. And this is what's called meta-learning. We're learning to build a system that will give us a good starting point that will allow us to learn from a small number of examples for each case. And so this is the upper loop in here. We've got an inner loop that corresponds to our learning from a small number of examples task, and we've got an outer loop that updates the, if I do have a pointer here, maybe, do I have a pointer? No, I don't have a pointer. What the F theta in the middle here are the starting point system, if you like. And so that's the thing that we want to make that as close as possible to all the other examples. So if we look at how the performance of that worked on some of the examples, there's quite a lot of numbers here. It's probably easier to look at it on the poster. But if we look at the far side, which is the sort of summary measure, and if you look at the ones in red, what you can see is the pre-trained example, which is just a standard training system. It works fairly poorly on some of those rooms, the ones highlighted in red. And even with a little bit of fine-tuning, which is quite common, it doesn't improve it very much. But if instead we use the meta-learning process, we get much better performance improvement on that. The only other thing to say is it doesn't always work. So if the performance was good to start with, it may not help you. So we can discuss more. And if you're interested in finding out more, come and look at the poster. Thank you very much.
Hello everyone, I'm Daiki Takeuchi at NTT Corporation. I'd like to talk about audio difference captioning, which is the extension task of audio captioning to describe the difference between audio. Firstly, I'll talk about background and problem. Audio text cross-modal tasks, including audio captioning, have been widely studied, and this connects audio and captions, like this example. And this example has two audio. First one is like that. And second one is like that. And from caption, we can understand both of them have rainy sound, but second one has only dog bark sound, and it is only once dog barking. How about this example? The first audio is that. And second one is. So in this example, second one is more harder rainy sound, but this caption did not describe this. So we can understand just by reading this caption. Both sounds are hard and constant rainy sound, but we cannot understand what is the difference between them from caption. So we think the problem, slight difference, are often not described by conventional caption. To solve this problem, we propose audio difference captioning called ADC, which is describes the difference between two audio clips. So previous example, by difference captioning system, we can get difference caption, and we can understand just by reading it. The rain second one is louder. So we think ADC has potential to distinguish similar sounds. And this is summary of our proposal. First proposal is definition of ADC task. And we also built the audio diff caps dataset for ADC task. And second one is a system for ADC. Our proposed system has two techniques. And first one is cross-attention concentrated transformer, which use only cross-attention to extract difference efficiently. And second one is similarity discrepancy disentanglement called STD, which is auxiliary loss function to emphasize subtle differences. And bottom table is brief result of our experiments, and proposed system improve all metric scores. So, at the poster session, I'll talk about more detailed. Thank you for your listening.
Okay, hello, I'm Manu Harju. My shirt is screaming that I'm from Tampere University. I'm presenting evaluating classification systems against soft labels with fuzzy precision and recall. So we say that hard labels are the binary labels, and with soft labels we mean any labels that can, or labels that can take any value from 0 to 1. These kind of labels can arise synthetically from, for example, mix-up or label smoothing, or they can come directly from the annotation process, like they can represent the annotator confidence, or they can be aggregated from different annotators' opinions. If you want to use the existing precision and recall and F-score with this kind of labels, we need to binarize the reference data at first. And actually that's a bit difficult, at least compared to the binarization of the system outputs, where we can tune the operating point according to our preferences towards the false positives and false negatives. So our approach is that we interpret the soft labels as we take the predictions and references as fuzzy sets, and then we just interpret the soft labels as the membership values to those sets. And then we use the standard definitions of precision and recall and F-score and just use the fuzzy sets instead of normal sets. And by this, we have an extension of the standard metrics, so that with binary labels, we still get the same definitions. Here are two small examples. On the first row, on both cases, the blue denotes the predicted values, red denote the reference labels, and then without any better knowledge, we use the 0.5 as threshold value, which is denoted with the dashed gray line. On the first case, half of the points are classified correctly. We get 0.5 F-score with the binary case. However, in the second row, all the predictions are quite close to the reference labels, but they just happen to be on the incorrect side of the threshold line, except the last one, which is a true negative. But it doesn't help in this case, so we end up having a hard F-score of 0. On the other hand, this soft F-score manages to catch the difference. In the paper, we evaluate the method with the DCASE challenge data and baseline. We do some modifications to the baseline model and also some random methods or data sampling to get some random system outputs. Results show that our rankings are quite nicely correlated with the rankings made with KL divergence, suggesting that the method is quite good for measuring how well the system outputs are following the reference labels. Also, we get smaller confidence intervals than just binarizing the data and using the hard metrics. Thank you.
The full screen. Sorry? Oh, thank you. So hello everyone, my name's Andy. I'm a PhD student at the University of Southampton, and my talk my talk today is entitled Bioacoustic Event Detection under Domain Shift. So just as an introduction, normally in machine learning, we assume that your training data and the data that the machine learning model encounters when it's deployed follow identical probability distributions. However, in practice, this often doesn't hold due to dataset biases, and we call this domain shift. So these kind of dataset biases are particularly common in passive acoustic monitoring and bioacoustics because of the nature of the way data is collected. You can get quite significant differences in data collection or environmental conditions between different acoustic monitoring programs. And in the end, this manifests in a significant underperformance of your models from the in-distribution data, which is what you'd get if you simply hold out a section of the training data, and then your out-of-distribution performance, which is the performance on the new data sets. So the questions we're trying to answer in our research is how do these models perform in these more challenging scenarios of domain shift, and then how can we maximize the performance in these scenarios. So to do this, we introduced a new benchmark for out-of-domain performance based on detecting humpback whales in underwater acoustic data. We collected data from 9 different domains which in this case are different monitoring programs, which include humpback whale calls in different locations all over the world. And we can expect these different monitoring programs to have different distributions in things like signal-to-noise ratio, environmental conditions, a set of non-target events that occur, recording method and equipment's propagation characteristics, and so on. So then we use this benchmark to evaluate a few different existing baseline detectors, including template matching and the current state of the art, which is a ResNet model, which is trained on a huge data set of 200,000 hours of data, albeit from a single monitoring program, and then a simple CNN architecture that we design as well. And throughout, we use what we call the outer distribution or outer domain testing setup, which means we're training and testing the models on disjoint domain sets. And as part of our analysis, we also vary the number of domains in the training data and also compare one possible solution to the domain shift problem, which is commonly proposed, which is unsupervised domain adaptation. In particular, we test a bunch of algorithms which perform test time adaptation, shallow test time adaptation to the new data. And when you put all the results that we gather together, you get a graph that looks like this. And so the key takeaways from this work, as expected maybe, the presence of these dataset biases make it much harder to capture the underlying causal patterns of your data generating processes, which whatever the bioacoustic event you're trying to detect, using only single domain data. And this then results in poor outer distribution generalization. And because it's a difference in the data distributions, this is regardless of the amount of data used. You'll never get that full distribution coverage that you would otherwise see if you just collected more data in another different kinds of tasks. However, the good news is that if you just simply pull data together from multiple different domains, which we find to be at least 6 for this benchmark, this can solve this issue, and this actually turns out to be both necessary and sufficient condition for achieving maximum performance on this data. And the consequences of this is that our simple model, despite having 10,000 times fewer parameters and 100,000 times less training data than the previous state of the art, it can significantly outperform that model. If you don't have data from multiple different domains, then you can use domain adaptation to improve out-of-distribution performance, although we notice this doesn't work all the time, and we do get a lot of negative transfer occurring as well. And finally, we want to give a special shout out to PCN, per-channel energy normalization, which we found to be probably the single best thing you can do to remove these spurious correlations from training data, and gives you a significant boost in performance as well. So thank you for listening. I'll leave you with these nice pictures of some humpback whales, and I hope to see you at the poster.
Hi, I'm Sanjeel, and it's great to be here and to talk about some of the audio research that's happening at the Meta Reality Labs. So let's get started. Our vision at the lab is to enable effortless listening and realistic acoustic rendering through multimodal egocentric understanding. And I think Andrew's talk set a very good context for the work that I'll be talking about. The goal for my talk today is to introduce you and highlight some of the open source tools that the team is building to enable this vision, and for this to be a beginning for us to continue to collaborate and contribute on some of the problems that I'll be talking about today. Since this will be a pretty dense talk, here's an outline. I'll talk about egocentric recording devices, and then highlight some specific examples of data sets and tasks for each of the different components of the vision that I just spoke about. So here, I'd like to highlight for egocentric recording devices, Project ARIA. that allows us to collect data from the user's perspective. So as you can see, when we talk about the user's perspective, we want to record the scene from the perspective of the experiencer. So the glasses form factor that you see over here is a very natural way for us to collect such data. These glasses come packed with a lot of different sensors, including 7 specialized mics, and GPS, Bluetooth, Snapdragon processor, and a lot of different multimodal sensors that add to its capabilities and make it a very powerful tool for us to collect such data in the wild. And this data allows us to then progress research on augmented reality and more generally on egocentric perception, egocentric machine perception in particular. And with that, I'll move to the second topic, which is around multimodal egocentric perception. And there we want to still be able to detect scenes, events, objects, actions, and interactions, but from the egocentric perspective. So for this purpose, we introduced the Ego 4D dataset, which is over 3,000 hours of uncurated first-person videos of daily activities. And this dataset comes with a set of benchmark suites, which is essentially tasks or challenges that also give you a glimpse into how egocentric perception could be useful. So starting from things about indexing past experiences to going towards analyzing your current interactions, which could be social interactions, from that to going to saying what action would you be performing next, right? So all of this, to do all of this, I think acoustic scene understanding is a central piece that we need to solve for. And as a demo example over here, you can do localization of sounding objects in egocentric videos, where ego motion poses a particular challenge that this paper tries to resolve. And they also propose sounding object labels for Epic Kitchen dataset, which is used for evaluation purposes. Moving on, towards effortless listening, we propose the EasyCom dataset, which allows us to record group conversations and solve for speech enhancement in the context of head-mounted microphone arrays. So this dataset was also part of the SPEAR challenge, and it comes with a lot of different annotations. In this case, face-bounding boxes, head-bounding boxes, speech activity, speech transcription, and so on. So if you're interested, please do look into this. And coming to the final piece, which is around realistic acoustic rendering, I will let this video do the talking here. So as you can see, these kind of platforms and data sets can be used to perform navigation and active source separation in unmapped 3D environments. And so these are some of the challenge tasks that you can go and see if you're interested. And final thing over here would be, this is hot off the press, audiovisual scene synthesis, which is essentially audiovisual nerve, where you're given an audiovisual scene recording and you want to be able to synthesize novel videos with specialized audio with arbitrary novel camera trajectories, right? So I'll play these videos to show some results and then finish the talk. So here you see right, so this was 360-degree rendering, and then you could be moving from left to right, which would be right. So thanks a lot for listening. So if any of this has piqued your interest, please come and talk to me. You'll see me around for the next 2 days, and I'm thankful to the team for allowing me to represent their work today. Thank you.
Hello, my name is Kalle Koivuniemi. I'm a principal engineer at Huawei Technologies, and I'm here to give you an introduction on our local Tampere audio lab and the team. So, the Tampere Research Center focuses on two key areas, imaging and audio. And we do both long-term research and a bit more like shorter-term things where when those technologies that we have developed mature, we then try to help the product programs to bring them into the market, into consumers' hands. And we do that, of course, in-house and also by collaborating with companies and universities. The camera lab looks at hardware and imaging and computer vision algorithms, and of course, image and video quality. On the audio lab, our focus has really been on wireless headsets, but we do other kind of wearable audio devices as well. In there, we look into voice and both full band audio algorithms and audio quality, hardware things, and wearing comfort. The challenges that we face, they relate to this kind of more wearable product platform. So a bit more moving away from the smartphones and going into kind of more mobile devices. Wearables are in your ears, they might be in your wrist, they might be the spectacles that you are wearing. And they get exposed a bit differently than just smartphones. So the key challenges nowadays are really in noisy environments and how voice quality functions in those kind of environments. And then how do we tackle those? We look at mechanical and algorithmic ways into wind protection, into understanding of human perception. Intelligibility, for example, is a key thing there, and reliable voice interaction with nowadays voice UIs. And of course, there is always this combination of ID and mechanical challenges to make things really, really small, and that faces other problems. Our team members typically have backgrounds. They are masters or PhDs from signal processing, AI/machine learning, software development, acoustics, mechanical engineering, hardware, measurements, or perceptual audio quality. And we, of course, like people who have like a general enthusiasm towards editing audio. Thank you. If you want to talk to us a bit more about the challenges that we face and what opportunities we can offer, our stand is right there outside this hall. Thanks.
Okay, thanks to all the presenters for the insightful talks. I've been instructed to tell you that the lunch will be served at 12:15 in the corridor. And the next spotlight session is at 1:30 here. And in the meantime, you'll have like plenty of time to discuss with the presenter around the poster just on the other side of the room.